Thanks everyone for making all the time to attend this presentation. As the title says, this is about inequality joins and pandas with Pyjanitor. A bit about me. My name is Samuel Oranyeli. I'm a data engineer, a Nigerian Australian living in New South Wales. I love open source. I'm a contributor to Pyjanitor and PyData table. This is an outline of what we'll be going through: intro, joins, look at the algorithms, performance, and future work. So let's start with some intro. Why bother about inequality joins? What purpose do they serve? Say you're a cloud engineer and you need to find out about revenue and utilization trends. Inequality joins is something that can help you with that. If you look at the question, it says look for a customer from the West Coast that rented a virtual machine for more hours than a customer from the East Coast but paid less. Now, we'll look at some other questions, but I want you to have a look at the trend as we proceed. So let's go to the next slide. I'm a retailer. I want to make profits. So as much as possible, I want to maximize my profits and reduce my cost of storage. Inequality joins help here. Now, I want you to have a look at the words there. You can see more than, less. If you remember from the previous slides, there was that same points there: more than, less. An inequality, non-equi, there's an imbalance. So keep that in mind when we talk about inequality joins. They are not equal. There is an imbalance somewhere. Tax audits. You want to find out who earns more but pays less tax compared to another employee. Inequality join comes into play. Again, look at that comparison. A greater than, a less than, a higher, a lower. There is an inequality. Same for events. For time management, you want to find out overlapping events. Again, there is an inequality in there. An inequality join can help you with that. But before we go further with inequality joins, what exactly are joins? At its simplest point, as the name or as the title says, a join is where you combine two data frames to form one. At its very naive point, a join can be a Cartesian join, in which case you're joining every row from one data frame with the other data frame. So if you look at the image, we have a data frame 1, a data frame 2, and then we're combining every one of them with each other. So you have about 9 rows altogether. That is, at its base, a Cartesian join. However, Pandas, SQL, engines, and all of that have found efficient ways to deal with joins. The most popular join is the equality join. You're comparing on something. So if you look at the data frame 1, data frame 2, we're saying, give me the rows where the values from the left column match the values from the right column. In this case, we can see that it's 2 and 3. Again, it's an equality join. This is not an inequality. Again, equality. There is no imbalance. This is equal to that. Inequality join, however, is either greater than, or it's less than, or it's not equal to. It's never equal. Another, or a synonym for inequality join, is a non-equi join. You could say a conditional join, but more often than not, you hear the words inequality and non-equi. So for this example, we're saying, give me the rows where the values from the left column in DF1 is greater than the values in the right column in DF2. And the orange bars point us to the rows that fulfill that criteria. A subset of the inequality join is the rolling join, in which case you're not interested in getting all the values. You want specifics. It's either you want the very first match or the very last match or the closest match. You find applications usually in time series. So for this case, we say, give me the very first match where the values from the left column in DF1 is greater than the values from the right column in DF2. In Pandas, because the focus here is on Pandas, the equality join is efficiently implemented. The rolling join is efficiently implemented. For the equality join, it's a hash join. The rolling join, you have to sort your join column, and then there's a form of binary search. The inequality join, however, is not implemented in Pandas. So what you have at the moment is you have a Cartesian join where you lump everything together, every row from your left data frame with your right data frame, and then you prune it down to just the values you want. Now, for small data size, relatively small data sizes, it doesn't matter. It's okay to go with that. But as your data size increases, it becomes inefficient, it becomes non-performance. And we need an efficient implementation for inequality joins in Pandas. I have to mention at this point that there is the interval index in Pandas that can help with inequality joins. However, it's only efficient when you don't have overlaps in your data. If there are overlaps in those intervals, you lose that efficiency. You essentially have to do a for loop to be able to pair your data accurately. The last one there is just how it looks in SQL. SQL is a wonderful language once you get used to it. So yes, as I said, we needed an efficient implementation for inequality joins in Pandas because of what it could help us to solve. And I just went ahead and implemented it in Pyjanitor. And the name of the function in Pyjanitor is conditional join. Basically, this is the API for it. And the focus for this particular slide is on the variable args, which is where we pass in the columns that we need to process. At its core, it's a tuple. So column from your left data frame, column from your right data frame, or a named series, and then your comparator. Your comparator can be greater than, less than, not equal to, and depending on the scenarios, it can even be an equal to or comparator. So what do? You do your pip install Pyjanitor, and then you import Janitor. Again, observe, pip install Pyjanitor, and then import Janitor. Pyjanitor is basically a port of a library from R, Janitor. The initial aim was to provide an API for cleaning data easily, but over time the goal spread and went further than its original intention. Let's look at some examples on the usage of the conditional join on data frames in Pandas. So we have df1 and df2. We have the values right there. If we run it with the Cartesian join or the cross join, you first build up your data frame and then you shrink it. That's what you have in cell 5. In cell 6, what you just have is your left data frame, your right data frame, and then your tuple. The tuple has the column from the left data frame, the column from the right data frame, and then what are we comparing on? So basically left greater than right. Let's look at question 1 where we're talking about revenue and utilization trends for, say, a cloud engineer. This involves more than one condition. East less than west, and the second condition, east greater than west based on revenue and costs. Create our data frames, and then when we compare them, the first one in cell number 13, a Cartesian join, you do that first, and then you filter your data to select your specific columns. Look at the formats in the conditional join again, your left data frame, your right data frame, and then you pass in your variable arguments, duration time, less than, rev cost greater than, and then you can pre-filter your columns from the left data frame, columns from the right data frame. Let's have a peek into the algorithms before we look at the performance and why conditional join is a better option when you're working with inequalities compared to a Cartesian join. At its core, the algorithm is based on sorting and binary search. There are some other optimizations that I did on it, but at its core, that is all it is, sorting plus binary search. So let's take a single inequality join. Taking the df1 and the df2 that we were looking at earlier on. This time around, we're saying, give me the rows where left is greater than right. So we find the positions, we do a slice, and then we get our matches. We have a look at the same inequality join. This time around, we're saying the left is less than the right. We get our positions, we get our ends, and then we'll move and then we'll capture our points. Again, have a concept of how this works. Let me take you back to the previous slide. We can see, again, take for instance the value number 3. We start from that end, we get all the values 0, 2, whereas when we're getting from left to right, we're moving in the other direction. It will play a bit of a part in the idea when we deal into multiple joins, specifically range joins. Range joins are the more popular multiple joins, multiple inequality joins that can be found. So basically you're saying maybe A between B and C, or A less than B and C greater than D. They are between a range, they are opposing operators. There are 2 implementations of the range joins in Pyjanitor. There's one that was implemented with number, one without number. So the first implementation I did was without number, and then I realized that I could get more efficiency by implementing it in number. One reason why we went for number is because Pyjanitor strives on simplicity. We want to make it easy for contributors to join and make contributions to the code without that high barrier in terms of maybe using some other language that might be hard for them. Number offers that simplicity, so we decided to go ahead with number. But let's look at this first one where we're not using number. It's based on an article by Vertica. Vertica is an SQL database company. And the whole idea is get your positions for the greater than join, iterate it to get your first position, and then compute your actual matches. One concept I want you to have at the back of your mind is it's all about it's all about reducing your search space. Performance is all about doing as little as possible. The less number of rows you have to deal with, the more performance your operation will be. And that is the whole idea, whether we're using the number version or the non-number version, the whole idea is I want to do less so I can do more. So let's take an example. We have df1 and df2. I want to find the rows where the value underscore 1 is between the value 2a and value 2b. The first thing we do is we get the positions for the greater than join, in which case we sort. The first one is we sort on value underscore 2a. For this particular range join without number, the right data frame is a driver. So we sort on the first column, we sort in ascending order. We get our positions, use a binary set, you get your position. So let's take for example, the value number 4. We can see that its position is 6. So everything above position 6, 4 is greater than that. Now, if we stop here, what we have to do now is go take the value number 4 and check each position within value 2b, all the way that's from 0 to 5, and find the rows where 4 is less than value 2b. For small data, that might not be a problem, but we want to be more efficient. Again, the whole idea is do less work as much as possible. And that is where the next step comes into play. Get the minimum position that value underscore 1 is less than value underscore 2b. So when we look at the value number 4, instead of us going all the way to 0 to do our search space, we find out that the very first point where 4 is less than value underscore 2b is right here. So our search space is reduced to just 2 points. So instead of us searching from 0 to 5, we're just searching 4 and 5. If you take the value number 7, we can see that its lower boundary is 6. When we come to value under 2b, we realize that the very first point where 7 is less in value underscore 2b is value 9, which is position 6. 6, there is nothing to search. We get rid of that. Again, we are pruning as early as possible, and we are dealing with as small as possible a search space as we can get. We'll do our computation, we'll do our search, and then we'll get our final results. There are some observations with this particular implementation. The iteration is a for loop, it's done within Python. And for fairly large data, it may impact performance. That's one thing to be aware of. The other part is when we get our search space, we blow it up so that we can compare, and then basically we're using NumPy broadcasting. Depending on the memory size, depending on the data size, that can impact memory. So these are things you should consider if you're doing conditional join without number. Let's look at the number implementation. It's also based on an algorithm. Again, I love open source. People have put the knowledge out there, they've shared it, and we owe a great deal to them by taking their knowledge, implementing it, and making it as performant as possible. So thanks to all those that have done all the research that I'm building on. The algorithm is explained in a publication. The link is on the slide. The whole idea is get regions for your left data frame, get regions for your right data frame, compare them. The regions from the left should be less than or equal to the regions from the right. If those conditions match, those are the rows that fulfill the meet our criteria, and then we create our data frame. Let's look at the example. Same example, value underscore one between value underscore 2a and value underscore 2b. For this algorithm, the driver is df1, the left data frame. Because it is a greater than operation, we sort value underscore one in descending order. This particular algorithm requires that the values from the left data frame should always be at the top position wise. What do I mean? Take for instance the value, let's say value 7. We can see this is value 7 right here. It's always going to be at the very top, and then the next value that is greater than is 3. So we have 2, 2, 2, region number 2, all the way down to 3. But when we get here, we realize that we have a value 2 that has a 3. We have value underscore 1 that has a 3. 3 isn't less than 3. So we skip it, and then we create a new region number 3 and proceed on forward, and proceed on it that way. Again, the value from the left data frame has to be position-wise at the top. We notice for the color-coded ones, that's 12 and 7, there is no value underscore 1 that is greater than 12 and 7. So basically, we discard. Discard early, reduce your search space. Again, that is the driving force here. Reduce your search space. We don't want to blow up our data as much as we can. Reduce our search space. The less work we do, the more we get. Moving on to the next one, we get our regions. So we now sort for value underscore 2, for value underscore 1 less than value underscore 2b. Now, because it is a less than operator, we sort the left data frame in ascending order. Again, we run the same process. Position-wise, the value from the left data frame should be at the top. So we have, if you look at that, 1 and 2 above 3 from value underscore 2b. So they have region number 2. There is no value from the value underscore 2b, that's number 1, where it is greater than the value from the left data frame. So 1 is not greater than anything from value underscore 1 in the left data frame. We get rid of it. The value number 7 in df1 is not less than any value in df2 for value underscore 2b. We get rid of it. Get your filter things out as early as possible, reduce your search space. That's, if you don't remember anything, just keep that in mind. Do less so you can get more. We've gotten our regions, region 1, region 2, and then we do the comparison. We do a sort because it's easier to do because we're going to use binary search. So it's easier to sort. It's easier when you sort it rather. So take, for instance, that color-coded one in region 1. Again, the idea is the region 1 values for df1 must be less than the region 1, less than or equal to the region 1 value, for df2, and the region 2 values for df1 must be less than or equal to the region 2 values for df2. So if you take, for instance, for region 1, the very bottom value there, 5, you do a binary search in region 1 of DF2, we can't find a position for it, so we discard it. Take the value number 2, the yellow coded value there. We can see that it exists in DF2 region 1, position wise, it's there. And at that point, we need to take the value from region 2 and see which of them is less than or equal to in region 2. So we have 4. Let's take as the yellow coded value. We have 4 over there, and then we'll compare it with 4, 5, 3, and 2. 4 is less than or equal to 4, 4 is less than or equal to 5, but it is not less than 3 and 2. So the only thing that we keep is the rows 4 that has 4 and 5. So have a look at it. The color coding should give you an idea of how the pairing is done. Again, reduce our search space. There is some optimization done within the code, but this is a generic overview of how it works. And then you get your results. One other advantage of number is the parallelization opportunities it gives. So once there's this p-range function, once you use it, and you have to use it appropriately, it works wonders in the right scenarios. One other option we have is equi and non-equi joins. It's a relatively simple implementation. All I just did was intercept Pandas internal hash join indices, iterate through the inequality conditions, and then create the data frame. So instead of creating the data frame and then filtering, I do the filtering and then create the data frame. Generally, it is faster. It might not be so in all cases. A long-term approach, a better approach would be to integrate this directly into Pandas, something similar to SQL's where clause. Performance. Why bother if it's not performance? So let's look at some examples. Your mileage might vary, so depending on your machine or what you're running your code on, but this is the machine that I ran it on. Let's take the question number 4. This is from DocDB. DocDB is an SQL I like to call it an SQL interface where you can run SQL queries on Pandas. It does much more than that. I'm just keeping it as simple as possible towards the Pandas data frame. This is from DocDB's repo. It's about 30,000 rows, and we need to get overlapping events. If you do a Cartesian join, think about it. 30,000 squared. That's about what? 900 million rows? Only for you to find out maybe 3,000 rows. That is inefficient. A conditional join offers you a better way to go about it. So anyway, we import it, we create the table. When you run it in DocDB, you get 18 milliseconds. When you run it without number, you get 700 milliseconds, and with number, you get 17 milliseconds. So we can see the performance right there. This is just an eyeball thing, just to see that the values match. Run it on the tax audits. This is 10 million rows. Again, think about it. 10 million rows, square that. That is a crazy amount that you want to do a Cartesian join for you to filter for. Again, thanks to the DocDB team. This is from their repo. Create a table. When you run it on DocDB, you get about 12 seconds. When you run it with number, you get about 3.6 seconds. It takes forever when you don't use number. So that's why you can find the non-number code here. And when you check the results, it's 98,000 rows. So imagine having to do a Cartesian join only for you to get 98,000 rows. It's inefficient. This gives you a better way to go about it. If you're doing the equi and the non-equi joins, this is pulled from Stack Overflow. It was a question from R. I adapted it to Pandas. So you have about 10,000, 20,000 rows from your left data frame, 100,000 on your right. When you run it in DocDB, super fast, milliseconds. When you run it in Pandas, you get about 3.6 seconds. That's with the conditional join. If you run it with the classic Pandas margin filter, you're hitting 7 seconds. So you can see that with the conditional join, you get some performance. And with DocDB, you get even more performance. Check the row output, 17 million rows. So this is just a row check just to be sure things match. And then I decided just to go crazy and say, let's just take out the equi join and see how far the program can push itself. When you run it with DocDB, you get 3 seconds. When you run it with number, with the conditional join, you get 12 seconds. When you run it without number, you get 21 seconds. Check the number of rows, it's about 267 million rows. Again, the idea is conditional join offers you an efficient way within Pandas to get results for inequality joins. Future work, integration into Pandas and PyData table. I feel for Pandas, the API has to change for it to be able to fit into Pandas. I also noticed that more often than not, joins are a means to an end. Aggregations or some other reduction operations follow up after a join. So the question is, should we stick in aggregations? Will it be more efficient? And lastly, I'm open to suggestions for improvements. If you have a look at the code and you feel there are things we can improve to make it better, please feel free to do so. Have a look at DocDB, our data table, dplyr, and SQL databases. These all have implementations for inequality joins, and they could even offer more performance than conditional join. At the very least, don't use a Cartesian join when there are better options. This links to that you can have a look at when you have the time. Thank you for listening.